Welcome, I am Faisal Waris, and today I would like to talk to you about how we can use ML.NET for machine learning in an interactive fashion with the F# interactive programming environment. So why ML.NET and why with F# interactive? So in my view, the first benefit is that if you have a .NET application and you want to embed some ML capability in your application, you can easily do so with ML.NET. Of course, the alternative is to deploy that capability as a service and expose that via an API and consume that in your application, which is a much more involved process. The second is that ML.NET is very memory efficient. Personally, I have run into many situations where using the basic Python setup, say pandas with the scikit-learn package, I couldn't handle the data sets that I was working with. It would just run out of memory. And that is an increasingly common occurrence with today's ever larger data sets. And now at that point, you really don't have much choice but to move to a different setup. That is not the case with ML.NET. The reason is that ML.NET can spool data from disk, meaning that it doesn't need to load the entire dataset into memory in order to train a model. So you can train much larger data sets with much larger data sets. Of course, it'll take longer, but at least you will be able to get the job done. ML.NET in that sense is similar to Apache Spark, but in my personal experience, I have found ML.NET to be much faster than Spark for training models on a single machine, and also the quality of the results is much better. Of course, if you have very large data sets, then you don't have much choice but to move to a distributed environment. But ML.NET gives you a kind of an escape route, an intermediate escape route. Personally, I use both Spark and ML.NET. Mainly, I use Spark for wrangling large data sets. Once the data is processed to a certain level, I can then switch over to ML.NET. The F# programming language has had this interactive capability ever since it was released almost about 10 years ago. Now, F# is not unique in having that capability, but that capability actually is quite crucial when you're working with data for machine learning or data science. It allows you to explore, visualize, and understand your data better, and then you can use that understanding to build better models. So this ability to use ML.NET in an interactive fashion with F# gives you an experience that's similar to, say, using Python with a Jupyter notebook. However, here we're using a much stronger toolkit with a strongly typed functional programming language backed by good tooling support. That, in my view, is a much richer experience, and hopefully you will agree with me when we look at this all working out later in this video. In a typical ML or data science project, these are the high-level steps that are normally followed. So you have data access and understanding, data pre-processing, model construction, algorithm optimization, and once you have a good model, interpretation of the model, and finally the model rollout. In this particular video, I will just talk about the first three steps, how you can use F# Interactive and ML.NET for data access and understanding, data pre-processing, and model construction. But at this point, I would like to mention that these three steps, the steps that are outlined by these two arrows, are iterative. The problem here is that you have several choices at each step, and the combination of those choices results in a kind of a combinatorial explosion. And in order to find the best settings at each step, you have to sort through a lot of different options and combinations. For example, like there's several ways of handling missing values. You could choose from several normalization methods or encoding techniques like one-hot encoding. There are several algorithms available that can be applicable for your problem. The combination of features that you might want to use in your model, that is also a big choice set. Then for each particular model that you might consider, there are hyperparameters, and what are the right levels of those hyperparameters for your particular problem or data. You know, that's a tedious and a time-consuming process to sort through all of that. So with the ML.NET, there's a feature called AutoML that helps automate the search through these choices. It's not a panacea, but it certainly reduces tedium and also time consumption. Now, so this is an important feature. We will not be talking about this today, but I would like to address that in a future video. Once you have a good model, you want to understand why the model is producing the decisions it is. Now, if you have what we call as a white box model, a simple model like a simple decision tree or a linear regression model, you can just inspect the model and understand how the model is working. But you have a more complex model, it's not possible to do that. So ML.NET also provides another capability. It's called per feature importance, and you can use that to better understand these black box models. And I would like to address that feature in a future video as well. So this is the setup for working with ML.NET in an interactive fashion. Here I have Visual Studio 2019. It's the preview version, and I'm using F# 5.0, which is the latest version as of now. So I have a Visual Studio solution which contains an F# project. It's one of the new SDK style projects. In this project I have two types of files. So the .fs files, the code in these types of files is compiled into the project output, the DLL or the EXE. And then I have these .fsx files. So these are script files. They're meant for interactive use. So here's a script file called packages.fsx. I will use this script to set up the environment whereby we can use ML.NET in an interactive way. Let's try to understand what we're doing here. So here we are referencing some NuGet packages. So this is new syntax. It became available with the latest version of F#. You can just reference NuGet packages directly in the script files. Unfortunately, there's an issue at this time where some of the native libraries in the packages that you reference are not available in the runtime environment. To address that, I'm taking paths to some of these native libraries and then adding them to the path variable, the environment path variable. I'm doing that dynamically here. So once this script runs, it'll set up the environment for us to use ML.NET in an interactive fashion. Now, at this point, I would like to mention that even though this is a script file, let's say I misspell a package name, Visual Studio will recognize that and immediately give me a red squiggly, indicating that there's no such package in the NuGet repository. A very handy feature. Let's also talk about the actual packages that we will use. So here I am pulling in AutoML from ML.NET. The reason I'm doing that is because this will pull in many of the other packages that I might need. So I only have to reference a single package. So makes the script a little shorter and easier to use. However, the model that we will build is a recommender model, and that is not included in AutoML, so I have to pull that in separately. f#.collections.parallelseq, I will need that for a little bit of parallel programming, and f#.plotly is for visualization. This package called mathnet.numerics. It contains many statistical functions and numerical functions. We will use that to do some density calculations. So I mentioned that we will be building a recommender model. Let's look at the data that we will be using. It comes from Kaggle, and it's the famous Netflix prize data set. It's about 680 meg, not tiny but not huge either. Let's go and look at the main data files. So these four files are the main data files, and the format is such. So you have a movie identifier as one line that ends in colon, followed by several lines where you have the user. So this is the user identifier, the rating that user gave to that movie, and the timestamp. Now the rating here ranges from 1 to 5, and the task is to use this data to build the model so you can suggest appropriate movies to any particular user based on the history of the movies that particular user has watched up until now. So let's see how we can process the Netflix dataset. I'm going to open a script file, mlexplore.fsx. So in the first line, I'm loading the packages.fsx script that we saw earlier using the special hash load syntax. So what I like to do in general is to keep the code that sets up the environment in its own script file, and then I can load that in other script files where I'm conducting different types of experiments. I'm opening some namespaces. This is like C# using statement. Pretty much the first thing you do in an ML.NET project is to create the context. So the context has some global settings and state, and it provides an access point for the functionality available in ML.NET, and we will see how it works a little later. So here I have saved the data, the Netflix data, into this folder, and I'm just getting the reference to the paths of the main data files, the combined data files in the Netflix dataset. So let me just run that. Okay, so here we have, so now it has loaded the packages, set up the environment for ML.NET to be used in an interactive way, and the data files variable or name is now bound to this array of paths to the Netflix data files. Now let's check if everything is set up correctly, so I'm going to write a line to test that. So data files, take the first file, pipe that into file.readlines sequence, take the first 10 lines, convert that into an array, and let's run that. Okay, so looks like everything is set up correctly. I am reading the first 10 lines of the first file. This is the movie identifier followed by the viewer rating lines. A little bit about F# syntax. So in F# it's quite common to use the pipeline operator. Essentially it takes the value on the left and feeds that to the function on the right, and this is a way of chaining functions together, and in this way you can write very fluent F# code. So the next step is to read and parse the content of the data files and turn them into a data structure that we can then use for modeling. Now there's a little bit of an issue here that we have to parse the files in a stateful manner. The reason is that we have our movie ID here followed by the associated rating lines. So we need to associate this line with the lines that pertain to it and that follow it. So how do we do that in F#? So I'm going to write another piece of code to explore this type of processing. Read lines, and here I'm going to use a function called sequence.scan. So I'm going to write some initial code and explain what this function does, and then we'll elaborate this code. So scan is a function that allows you to do stateful processing of sequences. It is parameterized, or it accepts another function. So this is an inline F# function and an initial state. So this is our state, which is a tuple of nones. What happens is that initially it's bound, the state is bound to this name, state st, and the item that is coming from the sequence is bound to this name L here. And this function should return a new state, and that new state is then threaded back into this function and bound to this name again, but at this time the item is bound to the next item in the sequence. So this is a way of threading a state through the sequence, and you can use that to do stateful processing. The output of scan is a sequence of states, and we will see that in a minute. So let me elaborate how we will process a single file using this approach. So if the line ends with colon, we know it's the movie header line. So what we will do is return the first tuple value as that line and the second tuple value of the new state as none. Otherwise, we will take the first part of the state and bind the second tuple value to the line. So I'm going to run this. So take the first 10 again and to show what it actually produces, and it'll be clear. Okay, so this is the output from running sequence.scan. So initially it emits the initial state, and then it's emitting this tuple, which is the movie identifier with nothing for the viewer rating. But then this is where it starts to make sense. So here now it's taking the movie identifier that's coming from the previous state and binding that to the viewer rating line. So now you see that you have associated the movie rating with the correct viewer rating lines. Of course, if you get to a new movie, it will then execute this part and will then substitute the first tuple of the state with the new movie identifier. What we will do here is that we will ignore any of the states that have that does not have sums in both parts of the state, and just and ignore the rest. So how are we going to do that filtering? I'm going to use another sequence function, sequence.choose, and do a little bit of F# pattern matching. I'll just explain explain this in a minute. Okay, so what choose does is a combination of map and filter. So if we return a value that is sum, choose will take that and ignore anything that is returned and then as a none. So choose accepts another function. So this is another inline function. Here we're using the function keyword to do pattern matching. So we're matching this pattern where both parts of the tuple are sum, and then we can deconstruct the tuple and extract the inner values and package them into a separate tuple and return that in a sum. Otherwise, we return a none, and this is the otherwise pattern. So let me run this. So this is the output. So now you can see that we are getting the content we are interested in without the extra optional stuff. So now that we understand how we can parse the files, let's look at some pre-written code. So part of the code is similar, but now I have defined a data structure. It's called view. It's a record in F#. It has 4 fields: the movie identifier, viewer identifier, rating, and the timestamp. So let me evaluate this. This is a helper function to parse out just the movie identifier. And then there's another function here called read file, which will read a single file sequentially in a stateful fashion, as we saw earlier. Okay, so what this will give us is a sequence of view records. So this is where we're creating the view record from the content of the file. And now we're defining a collection which represents the data in all of the content files. The way I'm doing that is taking the array of the file paths, feeding that to psequence.collect, and parameterized with the read file function. So here what psequence or parallel sequence will do is read each file sequentially, but all of the 4 files in parallel, and it will merge the individual data streams into a single data stream. So as you can see down below, the data value is bound to a sequence of view records. Now if so I've already evaluated this. It's also lazy, so it didn't actually do anything. In order to see if it's working, I'm going to execute this line, which is just pulling the first 100 records from that sequence, and as we can see, it is working correctly and we are getting the view records. Okay, so now we need to convert this data into something that ML.NET can work with. So the native data structure of ML.NET is iDataView or data view, and we can obtain that from our data of sequence of views by using this function called load from enumerable that is accessible via the data category from the context that we created earlier. So let me show you how we can access the functionality in ML.NET using the context value. So if we do context dot, you get a list of the catalogs. So these are called catalogs. As you can see, you have the data catalog, you have a catalog for anomaly detection, binary classification, and so forth. So under the data catalog, I have many functions available for loading different types of data or working with the data files or data formats. And here I'm using load from enumerable. So if I evaluate this, it will return immediately. I get an iDataView. So this is also lazy. But what happens now is that I can take this data and feed directly to many of the APIs that ML.NET exposes. So for model training or data transformations or different types of data pre-processing, we can use this data structure to accomplish all of those types of things. So next, I want to visualize some aspects of the data. Here I'm reading a single file in its entirety and saving that into an array in memory. I've already executed this line, so if I just evaluate this name, I can see that I have movie records. Now let me evaluate this to see how many records I have. So I have about 24 million. So this means that we have about 100 million records in the 4 files. That's too many for interactive visualization. So I'm going to sample from that. Here is the random number generator, and I'm using that to filter down to 0.1% of the records in the file. And in my view sample, I have about 24,000 records, so that's much more appropriate. So I want to understand the distribution. So what I'm going to do is project out just the rating values and then count by them. And what I get is this array of tuples where the first value is the rating and the second is the count. Now this information is better visualized, so I'm going to open fsharp.plotly and create a column chart. So Plotly has presented the chart in a browser window. On the x-axis we have the rating values, and on the y-axis the count of the ratings. As we can see that the data is skewed towards the higher end. So this is important information. In some cases that might matter and we may have to take some compensating actions, but here I don't think it matters that much, so we will leave the data as is. So now let's try to understand how the ratings change over time with respect to each other. In other words, obtain the rating distribution over time. So in the previous chart, we looked at the rating distribution independent of time. Here we want to understand the time aspect as well. In order to do that, I am calculating a baseline value, which is the minimum date in the data set, which happens to be 7th January 2000. I'm going to then group the records in the sample by the rating, and for each such set, sort it by time, and then for each rating in that set, calculate the distance from the baseline date in the number of days. So once I have this set, I can then estimate the probability distribution using this function called kernel density.estimate Gaussian from mathnet.numerics. Let me run this code and see what we get. So here we have several area plots, each one corresponding to a particular rating. X-axis is time and y-axis is probability value. So in that sense, each area plot represents the probability distribution of that rating over time. So this is Plotly, and we can interact with the chart, so I can hide and show the different area plots by clicking on the legend. Let's look at the plot for rating number 5. And so that's interesting. We can see that most of the ratings were given when between 2004 and 2006. We can also see kind of a hockey stick effect between 2003 and 4. This is probably when the Netflix subscriber base grew exponentially. So that's all very interesting information. Now, if I look at the chart for rating number 1, it gives me some interesting results. I can see a bimodal distribution. So as you can see that relatively speaking, the movies around sort of March or April 2004 were not that great in Netflix. It doesn't really affect what we are doing, but it goes to show how this way of visualizing and interacting with your data provides you additional insights that may or may not be useful, but I think they are crucial when you're doing machine learning or data science. Let's move on to model training. So in order to train the model, we will have to transform our data because we have two identity columns, viewer and movie. We can't really use these columns for model training. So what we have to do is create one-hot encoded versions of these columns. So how do we do that with ML.NET? So first what we're doing is creating a collection of input-output column pair objects using these pairs of names. So viewer is mapped to viewer key, movie is mapped to movie key. So the key columns will be the one-hot encoded versions, and we will use this information in the map value to key transform. So what is that? So that actually creates the one-hot encoded versions. It's accessible from the transforms catalog conversion and then map value to key. So we have our transform object. We fit the data to the transform, and then the resulting object we can use to transform the data to obtain a new data set, which we are calling data view 2. So I've already run this code because it takes a while to run. Essentially, the transform has to sift through the entire data set to correctly encode the values. So it takes about 30 seconds to run. So if I execute this line, what I'm going to see are the columns in data view 2. So each data view has a schema, and we can sort of introspect that. So here we have our 4 original columns, and then we have the 2 one-hot encoded versions. And as you can see, we have fairly large sparse vectors. So the movie key ranges from 0 to 18,000 roughly, and the viewer key ranges from 0 to 480,000. Okay, so now the next thing to do is to split our data view 2 into test and training sets. We're doing it using this function, train, test, split from the data catalog. And then we're going to create the trainer. Here we're going to use the matrix factorization algorithm. It's also known as collaborative filtering. I will not go into detail about the algorithm because the video will become too long, but you access that algorithm through the recommendation catalog, trainers, and matrix factorization. So here we're creating the trainer using these opts object, which supplies the values to the trainer. So what are these? Approximation rank is roughly the amount of information content in our data. It's an iterative algorithm, so we're supplying the number of iterations. Here we are defining a very large sparse matrix. So the movies are going across the columns and the users are going down the rows, and the intersection is the rating. So once we have our trainer, we can then fit the trainer to the data, but here we're supplying both the training set and the validation set. So let me run this. So the model will take about 20 minutes to train. So I will pause the video and show you some intermediate results and the final results. So here are some intermediate results. The algorithm is running. It's at its 14th iteration. So what we have here is the training set root mean squared error and the validation set root mean squared error. I'm not sure what these values are. And so both are going down, so that's good progress. But I also want to show you the memory consumption of ML.NET. So FSI NeCPU, that is the process that's running this code, and you can see it's consuming a fair bit of CPU, but the memory consumption is very stable. So this shows that ML.NET can work with large data sets without really running out of memory because it's spooling data from disk. Now here you do have the option of caching data in memory, and that helps when you have an iterative algorithm, but you don't have to do that, and you can just leave the data on disk and it'll read it from there. So our model is now trained. If we look at the validation set root mean squared error, we get a value of 0.8557. So let's compare that with the Netflix competition results. So going back to Kaggle and the Netflix prize, data set, if we scroll down to this area here, we can get to the original Netflix competition page. So that competition was held in 2009. It had a $1 million grand prize, and if we look at the leaderboard, so the best results that were achieved by this team called Belcor's Pragmatic Chaos was a root mean squared error of 0.8567. So our results actually compares quite favorably to the leaders at that time. And who knows, if he had ML.NET in 2009, we could have won the $1 million grand prize. To recap, we learned that ML.NET is a powerful new tool for machine learning, and we can use F#'s interactive capability to work with ML.NET in an interactive way. We can then use that to explore and visualize our data before we build and test the models. Also, Visual Studio 2019 provides good tooling support for F# interactive scripts. If you're interested, the code we looked at is available in this repo. I would like to thank you for your time and hope to do future videos on this topic on a regular basis.